Have you guys ever been to the opera? Well, it's a fantastic experience. On the first time I went, I brought my wife and we went to see Mozart's Magic Flute at the Royal Opera House in Covent Garden, and this was truly a fantastic experience. More recently, I was supposed to go and see the Nutcracker, but things unfortunately didn't go as planned. But as you certainly have seen the title of this episode, today we aren't here to talk about Tchaikovsky or even Mozart, even though I will certainly talk about Mozart in a future episode because there's so much to say about my favorite composer. No, what I actually remember when I went to see the Magic Flute was that we managed to book the last places, and after huge diplomatic negotiations, my wife agreed to come with me at the opera. And trust me, that wasn't easy. Anyway, I bought online the last tickets, and I'm not gonna lie, the places weren't really great. The music was outstanding, that's a fact. But there is the scene in the first act that I love above everything in this opera, which is, in my view, one of the most beautiful arias in this opera. The scene is when Princess Pamina meets Papageno, singing about love. And what killed the scene was I could hear Pamina, but not seeing her. Which was sad. The opera singer was also absolutely beautiful, and I would have loved to have the song and the view, but I had to twist to catch a glimpse of what was going on. But Pamina's voice covered about half of the song, and this was of a stunning beauty, and yet it remained invisible to me. Now, in today's episode, guys, I will be talking about the Princess Pamina of all astrophysicists. The one that gives them the biggest pain in the neck as they try to see it and they try to understand it, but no one has an idea as to what it looks like, even though we know it's there. As you guys, we live in a planet that is included in a solar system that is part of the Milky Way, and turns out that 75% of this entire Milky Way's mass, well, we have no idea as to what it is. Now, my dear fellow travelers of the unknown, please grab yourself a coffee and make yourself comfortable, and let me tell you today the story of the mysterious life and existence of the dark matter. Today's episode will be a little trickier. This is why I'm gonna actually start with a disclaimer. First of all, I am not an astrophysicist, I'm just a science enthusiast, and I would have loved to have been one. So I'm gonna try to explain this as clearly as I can, considering that this topic is something that more than one astrophysicist would love to understand. So the knowledge on these topics evolves quite constantly, and of course one day I hope we will discover the true nature of what is dark matter and dark energy. So this episode is written in November 2023 at the best of my knowledge, but what I'm saying today could become inaccurate or inexact in light of future discoveries. So what is dark matter? Well, let's imagine that I give you a balloon that has stuff hidden inside. This balloon can be indefinitely extended. I also give you a bottom of helium. So what you will do is you'll take the balloon and inflate it with the helium inside, and what's gonna happen? Well, it's pretty simple, the balloon will inflate. Dark matter, if you take that comparison, is the helium inside the balloon. Okay, but I talk also about dark energy, so what is it? Well, now imagine that after you inflate the balloon, it keeps inflating and you have no idea why. This is dark energy. The problem in all that is that Just like the balloon, dark matter accounts for nearly over 80% of the entire mass of the universe. But what is it? Well, we have no idea. And if we do know that this stuff is real, turns out that yes, on that we are actually quite sure. So, in order for you guys to understand what we're gonna be talking about today, I'll speak in example and metaphor. As the name suggests, no guys, I won't explain you what dark matter or dark energy is because no one truly understands what it is. What's quite paradoxical about dark matter is that we know it's there. We don't even know if we should be talking about even matter, in fact. And we calculated it, and we know that if it doesn't appear in our equation, then the result doesn't really make any sense. But if we have no idea as to what this is, we, however, have an idea as to what it is not. And today, we're gonna go through that together. Now, for you guys to understand everything, let's talk first about gravity. Because yeah, what is gravity? You may have cursed it when something fell on you, like a glass of wine accidentally dropping on your dress or suit. But what is it? Well, someone named Isaac Newton in England in the 17th century asked himself the very same question. He allegedly saw an apple falling off a tree, but this is apparently a legend. But either way, something clicked on his mind, and he gave us the famous Newton laws explaining gravity as a result. You certainly have learned it when you were at school. But this is on how we calculate the mass of an object that we can determine at what speed it will fall. But that's a problem. He based himself on Johannes Kepler, a German astronomer, who also understood back in the days that planets were turning around the sun. So controversial laws back in the days due to the strong influence of the church, but Newton finally explained that what could attract planets to turn around the sun could in fact be the same thing that makes an apple falling from the tree. And that discovery was indeed important, and still considered today as a major scientific discovery and advancement of the century. But like I said, Newton explained how it worked, but he didn't explain why it worked. Someone explained why it worked in Switzerland in the 1900s. From the comfort of his office, he was probably bored that day, and he looked at his window of the Patent Approval Office of Switzerland. From this morning, someone was painting the wall outside, and this guy was actually on a ladder. Lost in his thoughts, in some sort of strange questioning, he started thinking, let's imagine that this guy suddenly falls from the ladder. What would fall first in terms of time? Is it him, or is it the pencil he carried, or the painting pot next to him? And then it all clicked, because during his fall he will travel through space, so from the top of his ladder to the floor, and time, because it will take him a certain time to fall. And in the end, nothing would fall first, everything would fall at the same time, it would impact the ground from the moment it started falling. And then we say that civil servants are lazy and on-the-clock employees, well, this guy would definitely prove you wrong. This guy was Albert Einstein, and times after his deep thinking afternoon he penned the very first draft of what would become a major scientific discovery, the theory of general relativity. General relativity explains that gravity is in fact linked with space and time, and it's all about that in the end. How it works is pretty simple. Let's imagine that Earth is a ball, and this ball is on a carpet. This carpet is the space. Now let's imagine that you make the ball starting spinning on itself at a certain and constant speed. What's gonna happen is that over time the carpet near the ball will slightly twist all around this ball. And that twist is in fact the gravity generated by the ball when it started spinning on itself. Pretty simple, right? Einstein's publication was a massive breakthrough in science back in the days. and even today, and paved the way of a clearer understanding on how the universe worked, and led us to create fantastic new things, and more importantly, explained everything that we failed to understand. And since we knew it was all about time, and that space and time was both very closely linked, we also understood that nothing, absolutely nothing, can travel faster than light in space. This is the calculation of the equation that you guys surely have seen somewhere, the famous E equal mc2, which is the calculation of how much mass will it require in order to travel faster than light. And why do we say faster than light, by the way? Well, what we call light in science is actually called a photon. And a photon is a small particle, or at least it has no mass. And there's nothing smaller than a photon of light. So what object with mass could go faster than something with no mass? Well, nothing, or at least for now. So now, perhaps one of those summer days you were outside, or at least out of a big city, and lying down in the grass, you looked up during the night at the stars and said, well, it's far away. And you probably piqued your interest as to how far this star could be compared to Earth. And you found that this star was at a certain number of light years away from Earth. I know, I'm doing that with my wife when we're in France because we've got a clearer sky and it's magic to be lost in the immensity of space. And you are probably dazzled by the fact that that star was, let's say, 10 million light years away from you. And you were like, wow, it's far. And probably wondered why a light year away meant, actually. Then you told yourself that a light year is the distance this light, so the photon we've been talking about, travel through space to come to your eyes and be absorbed. And you were right. And it's here that things make sense. During those 10 million years, or these 10 million light years at least, in the photon's point of view, well, no time actually happened since this photon was traveling at the speed of light but in space. So what that means is that from the moment it was emitted to the moment it was absorbed, technically no time happened for it. And it was not even born that it was already dead. But from your point of view, because you cannot travel faster than light but in time, well, then you were the lucky one to see this photon to be absorbed, and you were the lucky one to see the star shining. Now it's kind of poetic to say that, but in summary, when you look at the sky in the night, well, in fact, you're looking in the past. Yeah, think about that when you're looking at a star in your garden next time you're doing it. But now let's talk about something we all experienced once in our life. It's called the Doppler effect, named after a Danish scientist, Christian Doppler. What is it? Well, it's precisely that. So, what that means in here is that when an object moves in space, it compresses the waves before it and, as a result, extends the one that trails it. In a nutshell, when the siren you heard was coming closer to you, its sound seemed more low-pitched and seemed like a normal siren. However, when it passed after you, the sound, as it was compressed in front of it, left the high-pitched trail, and that's a result why you heard in a lower pitch. But of course, the Doppler effect does not only apply to sound. We discovered it through the sound, indeed, but that's the only observable way that we have when we discovered it. But it actually does apply to light. Again, we're back in time and space. See? Science is amazing. Everything is connected. Now, if you guys aren't already sleeping by the explanation I've just been doing, you paid attention to when I said, when you look at the sky in a clear night, you look in the past. You know, stars, those little white or yellow dots forming drawing in the sky. Yeah, you see them yellow or white or whatever, but guess what? They aren't white at all. No. And in fact, they are actually blue or red. You see them white because the Earth's atmosphere makes you see them white, but the reality is different. And it's someone else named Edwin Hubble who explained it. Hubble, if you know a bit about astronomy, is the guy who gave his name to the famous telescope that brought us fantastic images of the cosmos. But Edwin Hubble was just another scientist who made major discoveries on our understanding of the universe. And amongst the plethora of stuff he discovered, he actually determined that when you see a star with a red glow through a telescope, what it actually means that this star comes to you. Well, not to you personally, but it comes closer to us on Earth. On the contrary, if a star has a blue glow, well, it means that this star moves away from you. But of course, since we talk about things moving in the universe, we are talking about huge and tremendous speeds. So now you're gonna tell me, okay Taylor, fine, but what does all this have to do with dark matter now? You remember when I said that thanks to the general relativity theory, we could start to measure the mass of objects, galaxies and other stuff? Back in Switzerland, yeah I know there again, in 1933, an astronomer named Fritz Zwicky took samples of galaxies located in the Coma Berenices constellation and started doing the math. Don't ask me how we did it, but the idea was how we calculate the mass of the entire galaxy so we could determine how much weight our galaxy, the Milky Way, actually weighs. But Zwicky had, let's say, a certain attitude towards his colleague, and the thing made that, well, let's say, it wasn't that much in good terms with loads of his colleagues. And what happened was, once he did the math, something didn't add up quite right at all. The values he found as a result of his equation were 100 times more than predicted. Long summary, a pretty bad variance. But like I said, Zwicky was not liked by loads of his colleagues, so his work became in the end quickly dismissed by almost all his colleagues, and everybody argued that because of error calculations he could never have found the correct result. But this was not calculated either. And no one did really do the math to get the actual result. You don't want to help a colleague that you hate, don't you? But what if he was actually right when he did the math? No, instead of that, in 1960s, technologies evolved and we could now use the radio. And we started using radio telescopes to observe and take pictures of the universe. In fact, the Roswell affair wasn't very long ago, and as everybody was looking for alien life, whilst the US government was actually spying on the USSR in the middle of the Cold War, a coalition of scientists launched the SETI project. So SETI stands for Search for Extraterrestrial Intelligence. And you get the idea. It was all about listening the sky and search for aliens. But not only. As they started pointing their telescopes in the sky, apart from a signal that would remain famous as the wow signal, that I will definitely talk in a further episode, probably in a future season, they actually observed something that didn't make any sense at all. On the outer region of galaxies, stars were spinning at an equal speed as they were spinning at the center of the galaxies. And that did not actually make any sense at all. So now, do you remember why I explained gravity at the beginning? Well, here we go. Newton and Einstein taught us that when a body starts turning on itself, it writes the space-time around us and creates gravity, and at the same time, Doppler and Hubble told us that when an object glides towards us or away from us, it emits either a red or a blue light. So now we faced another problem. Because if the universe was stable and static, then why did stars on the periphery of the galaxy would turn at the same speed than those to the center of the galaxy? It didn't really make any sense, did it? So, coincidence? No, absolutely not, and this will pave the way to something that will become one of the greatest scientific mysteries ever. Because if all the stars within a galaxy are all turning at the same space, whether they are close or in the edge of the galactic center, well, that is the evidence that the universe is actually expanding. And that wouldn't really make any sense otherwise. And now, everything kind of made sense. Between Zwicky's calculations, the observations, there was something. So we did the math again, and again, and again. And they try to remove that mysterious thing from the equation, because after all, it's probably just a coincidence. And turns out that trying to remove that thing and all the math and the calculations would ultimately be wrong. And if we added it, well, everything matched again. So what's that thing? Astrophysicists call it dark matter and dark energy. And why dark? Because we have absolutely no idea as to what it is. And we aren't even sure if we should talk about matter and energy. Now, let's talk about the basics. Dark energy and dark matter are not the same thing. Dark matter is something that we know accounts for about 80% of the mass of galaxies, ours included. And dark energy, it's the energy that makes the universe inflating. But we know that it's here. We know that universe expands through calculations and observations, and we know that something is expanding the universe. But what causes it? We actually don't know. Is dark matter and dark energy related? It is apparently unlikely, but not excluded. At this hour, what these are, we strictly don't know. The only thing we know is that they are here, and without this, we cannot make accurate calculations of galaxies and understand what and why the universe is inflating. But we may not know what it is. We do, however, with a certainty, know what it is not. And that's what we're gonna see together today. But let's go first on what we know about dark matter. First and foremost, it does make sense, but dark matter is of course not ordinary matter or baryonic matter, since it is not made up of the atoms and molecules that forms the ordinary matter that we encounter in everyday life, like gases, dust, planets, stars, or living organisms. Like I said before, we don't even know if we should call it matter. It does not emit or reflect light, unlike stars and planets which absorb or reflect light, or any other forms of electromagnetic radiations, which is why it cannot be seen directly using optical telescopes. It was not detected directly. Despite extensive research, dark matter has not been observed directly, and its presence and properties are inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. We also know that it is not uniformly distributed across the universe. It forms complex cosmic webs with dense regions forming some sort of gravitational skeleton that galaxies and clusters appear to be built on. It is also not the same as black holes, as they are also invisible and detected by their gravitational effect. They are objects of extreme density formed from collapsed stars and other processes. Dark matter is thought to be more diffusely distributed throughout the universe. We also know that the current standard model of particle physics, which explains fundamental forces and particles, does not include a particle that could account for dark matter. It suggests that our understanding of physics might need to be extended. And finally, it does not explain at all any cosmic phenomena. Even though it is crucial for explaining the rotation rate of galaxies and the motion of galaxy clusters, it does not explain other phenomena, such as the nature of dark energy or the specifics of black holes formations. Now, regarding what we know about the little brother, first, we know that dark energy is not dark force. Okay, the name might suggest it, but dark energy is not a force in the traditional sense like gravity or electromagnetism. It does not push or pull objects in a directional manner. It is not dark matter either, because while dark matter contributes to the mass of the universe and affects the motion of galaxies and clusters through gravity, dark energy is thought to drive the expansion of the universe. It is not a known energy form. Dark energy is not a form of energy that we might encounter in everyday life or in known physics. It's not like electricity, nuclear energy, or chemical energy. It is not visible or detectable directly. We can't see or directly detect dark energy with current technology. Its existence and property are inferred from its effects on the universe expansion and cosmic structures. Perhaps we shall detect it in the future. We also know that it is not static or unchanging. The understanding of dark energy could evolve with new observation and theoretical developments. it is not a static concept in cosmology. It is not necessarily constant either, which implies that dark energy has a constant density throughout space and time. It is not definitively established. Its property could vary across space and time, and in the end, it is not a solution to all cosmic mysteries. Because dark energy helps maintain the accelerated expansion of the universe, it does not, however, answer to all the unknowns in cosmology, such as the nature of dark matter or even why the Big Bang occurred. But we know it's there. We can calculate it and we can see its effects, so from a mathematical point of view, it's impossible to ignore. So we started making hypotheses as to what it could be. For dark matter first, the first suspects are what we call WIMPs, for example. So I know when it's said like this it's a bit rude indeed, but WIMP is in fact an acronym for weak interacting massive particles. This hypothetical force interact with gravity and possibly weakly with other particles, but not with electromagnetic force, making them invisible to light-based observing technologies. But there is not enough evidence to sustain this. Amongst the other candidates are also the axions. It's another theoretical particle and they've got a lot in common. Axions are extremely light, much lighter than neutrinos. They are hypothesized to solve certain problems in particle physics and could be a component of dark matter. Now, what's an axion, you're gonna ask me? Well, think of another super tiny particle. It's pretty much like a secret agent particle that nobody has ever seen. Scientists think axion could be floating all around us, but they are very good at hiding. They are so good at it because they are incredibly light and they barely ever touch anything else. Like dark matter, axions are really hard to find. So they could be a form of it, but again here, no evidence. But as we talked about axions, as I mentioned its name before, we've got another suspect called the neutrinos. What is it? Well, it's pretty simple. Imagine a tiny particle that is so light and that it can zip through walls, mountains, or even the entire Earth without stopping or even touching anything. I know physics can be really funny sometimes. Neutrinos comes from the sun or other stars from space and they are always moving around us. But we can't see them or feel them because they are very shy and hardly ever interact with other particles. But whilst it has been widely eliminated that dark matter could be neutrinos, it remained that it could actually still be a specific category of sterilized neutrinos, like a type that interacts only via gravity, making them again another potential candidate for dark matter. Unlike regular neutrinos, they do not interact via weak nuclear force, so there's still potential there. Or that could also be MACHOs, another funny acronym for Massive Compact Halo Object. Yeah, I know scientists love funny acronyms. Between WIMPs and MACHOs, we've got for all colors indeed. Anyway, what's a MACHO in science? In a nutshell, it's a plethora of stuff that includes objects like black holes, neutron stars, or brown dwarfs. They are massive enough to exert gravitational effects but do not emit light. However, extensive researches have provided limited evidence for MACHOs. So, back to zero here again? But since we talk about this, it could also be primordial black holes. These hypothetical black holes formed soon after the Big Bang and could account for dark matter. Unlike black holes formed from collapsed stars, it could be of various sizes, including very small ones. But we would be surrounded by black holes in this theory, and again, no evidence. Or perhaps understanding dark matter could in fact change our perception of the world we live in and perhaps update the current gravity theories that got already established. Some theories propose modification to our understanding of gravity which could explain the gravitational effects attributed to dark matter without invoking unseen matter. This could make sense since Einstein explained general relativity in 1905, but he also predicted the existence of black holes that we never thought it could actually exist. The latest theory Einstein predicted and that got verified was the gravitational waves, so perhaps in light of future discovery we will have the key to decipher the enigma. Or perhaps in Einstein theories, there is something big that we simply did not see. But a lot of theories have been evoked, such as a hypothetical superfluid dark matter, a theory that combines aspects of particle physics and condensed matter physics, suggesting dark matter could have superfluid properties under certain conditions and therefore influencing galaxies' rotation. Or self-interacting dark matter, a model that proposes that dark matter particles interact with each other through forces other than gravity, which might explain some observation of galaxies that don't align well with the traditional dark matter model. Or composite dark matter, where dark matter is made of composite particles similar to how photons and neutrons are made of quarks. Or possible dark photons, analogous to photons in electromagnetism. Dark photons would be the force carrier for dark matter, interacting with it in a similar to how light interacts with ordinary matter. But for now, all we know is that dark matter surrounds us. It's everywhere, and it's something we can't ignore. It accounts for nearly 80% of the mass of the galaxy, and this 80% remain completely oblivious to us. Now, to conclude this episode, I would like to bring up something for you guys to meditate on. When scientific discoveries are made, a scientist, in order to remain credible when they will be asked about their discovery, will always try to prove the fact that their discovery is in fact wrong. Why do they do that? Well, it's actually to make sure that when their discovery is in fact true, it's because it cannot be proven otherwise. It takes years sometimes to find even the slightly accurate thing, something that does make sense in the discovery, and in the end, when it's confirmed, it's the moment for the scientists to publish their discovery and share it with the community and the world. Now I'm gonna ask you something. Do never say that you are sure of something until you completely are. As dark matter and dark energy serves us as the perfect example, always say that it could be unless proven otherwise. No one can be really sure 100% right now to have found the true nature of dark matter. Unless obviously this person is scheduled to be published in Nature very soon and set to receive the next Nobel Prize. Always gather evidence of what you're saying, because it's never funny to be proven wrong. As we wrap up this journey through the shadowy realms of the universe discussing the enigmatic dark matter, we are humbly reminded of the vastness of the unknown that lies beyond our current understanding. Dark matter, an unseen force holding galaxies together, yet eluding direct detection, challenges our perception of the cosmos. In the grand scheme of things, it represents the immense mystery that is our universe, an ever-present reminder on how much is still left to discover. As you guys reflect on the cosmic mystery, I invite you to share your thoughts in the comment section down below. What might the unraveling of dark matter's mystery tell us about the fundamental nature of reality? Until our next rendezvous with the enigmatic and the inexplicable, keep your minds curious and your eyes to the stars. See you next week, fellow travelers of the unknown. Hello guys, it's Taylor again, but this time off script. So thank you very much, first of all, for having listened to this episode, and I hope, like the previous one as well, I hope that you enjoyed it as much as I enjoyed recording it. and writing the script. But basically this episode, so if you guys want to know, like I wrote this episode when I was waiting for the tube to go to work actually on November 2023, and at the same period someone very famous, I mean, you know, this person died, and his death affected me personally because he died basically in the outcome of his addictions, and I had the same problems with my father. My father died of his addictions, and I will certainly talk about it on my blog or somewhere. And this episode is a bit of a tribute to him, so you know him, it's Matthew Perry. So Matthew Perry was, for me, my favorite in the Friends series. Chandler, it was like always, I loved him. He was actually the one who all the time I was laughing of his jokes. And when he died, I've been really affected because he struggled with mental health problems and he struggled against his demons, and that's why I wanted to pay him a tribute, because it affected me like personally, like on the time he died, and I was really, really feeling down. And that's why I actually wrote the episode on the dark matter, because I wanted to be reminded of, you know, the immensity of the universe. But the thing about Matthew Perry was that, so I read a story about him, like when he was actually doing Friends, when he was like performing for Friends. Sometimes it happened that the scenarists of Friends were running low on ideas, and it was always the person who was asked, you know, to come up with something, to bring up some new ideas, not because he was the best. I'm not gonna go into that debate. But because he had ideas. And recently, I actually watched something of, it was in YouTube, and it was an interview that he did with Ellen DeGeneres, I think it was. And he actually said a joke on this particular time, and this joke had the particularity to be like, I mean, to me it was funny, but apparently it's like 50% of the people who hear the joke would laugh, and 50% of the people who would listen to that joke would be like, okay, fine, fair enough. So I think that's because, you know, it goes like with the theme of dark matter and scientific mysteries. So I'm gonna try to do that joke, because that one made me laugh, and probably 50% of you would actually laugh, and 50% of you won't laugh. But I think it's good to, you know, finish the episode with this. So that's the joke. So that's the story of a guy. He's actually walking down the street, and the thing is, above his head he has like a big peach, you know, like the fruit, you know. And so he walks down the street, and there's someone, you know, coming to him, and he's like, excuse me, my friend, sorry, but do you know you have like a big peach above your head? So he's like, yeah, I know that. And the other guy is like, but how comes you have a peach above your head? Like, I mean, it's not comfortable. It's but how did that happen? So the guy with the peach on his head like starts, you know, like telling the story. So last day I was actually going to work, you know, and you know, I found like one of these lamps, you know, like when I was like on the street. So okay, I was curious because, you know, you don't see these things like very often. So I took the lamp, you know, and I started scrubbing on it like fries, you know, like as apparently we do, you know, like in these things. And suddenly when I scrubbed the thing, a genius came out. So I was surprised, you know. A genius came and he told me like, tell me 3 of your wishes and I will make sure that they will come true. So I was like, okay, fine. So I put the lamp on the ground, and I was like, okay, let's try after all. So I would like to be a millionaire. Listen, I didn't even finish saying the word millionaire, that there were guys, coming all around, like from everywhere, like with like this big cash, like these big cases of cash. And they were like, come on, it's for you, just go, take it. So I was like, wow. So I was inspired. And then after I asked, like, I want, like, the most beautiful woman of the planet to come right now and fall in love with me. And listen, same story. I didn't even finish that. That Scarlett Johansson came out of nowhere and she was like, oh my god, I love you, blah, blah, blah. So the last guy, next to him is like, wow, okay, that's impressive, actually. And, okay, but what was your third wish? So the guy with the peach on his head is like, well, the third one was something very silly that came out, I just wanted to have a peach above my head. See you next week, guys.